Thank you. So before I start, I'd like to introduce you Strings 2013 next year. It will be hosted by our friend in Korea, by this organization. And please take a note of the time. It will be in the week of June 23 to 29, 2013 in Seoul. And let's see. Okay, so let's see if this is working. Curious, it's not working. Why is that? Oh, okay, good. So these are a list of organizers that who will be hosting us. So now I'd like to go to the main part of my talk. Chukyu parol Esperanto. I guess nobody speaks Esperanto today here, so I'll just use English. So, not all Japanese speaks Esperanto. So first of all, I'd like to thank the organizer for organizing this conference, and also asking me to give this summary talk. So in fact, this is my third summary talk at the Strings in Paris, CERN, and Munich, and I realized that it's actually happening at every Olympic year. I don't know what it means. But. And so I thought that since I'm doing this for the third time, so I thought it would be a good idea to compare the Three Strings Conference and see how much progress we have made in the past 8 years. And so let me start with my first observation. Maybe I should stick here. So first observation. So when I was first asked to give this kind of presentation in Paris, so I was the last one to give the summary talk, and I thanked the organizer, and that was it. But then it's a bit different in the last two conferences. So at CERN, I gave the summary talk, and then David Gross gave the vision talk. And then again, here I'm giving the summary talk, and David is giving the vision talk. So I wonder what it means, and the only explanation I have is that after this experience in Paris, the string theory oligarchy decided that I need adult supervision. And I think that's what happened. And also, I mean, this is a rather sort of daunting task for me. So when I was asked to give this summary talk, I asked several people who have experience what I should and should not. And there was one that I was particularly impressed about. I don't tell you who said that, but when he said, when I gave a summary talk, I made a mistake of summarizing a talk that was canceled. So I tried very hard not to do that. So first I'd like to talk about the scientific talk that has been presented. And I'm particularly thankful to Yuji Tachikawa, who collected the slides of the past conferences so we can consult. And so this is actually a very good resource. So there have been actually excellent review talks on ADS-CFT applications, higher spin, perturbative amplitude, spring phenomenology, LHC physics and experiment, and alternative gravity and topological string. So I'm not going to summarize these review talks because it does not make sense to summarize review talks, but I will probably touch upon a few of these. So let me start with applied ADS-CFT because there has been a lot of interesting progress going on in this area. And this really demonstrates the power of string theory as a tool in broad range of tools in theoretical physics. So let me remind you that actually this was just begun at the Strings Conference in Paris, where Faroni started talking about the confinement in phase transition, but this was still at a rather formal level. And then real application started around this time when ADS-CFT was used for QCT, although of course the pioneering work was by Son Starinet that date like 4 or 5 years back. But now, this year, the application to condensed matter physics was much more featured. And for example, Shamit-Katil gave a very interesting class of solutions where dynamical critical exponent and hyperscaling violation and the entanglement entropy can be seen. And I myself actually was amused to learn that the solution I looked at with Nakamura and Park is actually an example of Bianchi 7. Iqbal gave a very interesting talk where the prediction of Lattinger theorem was actually reproduced by computation of monopole instanton in three-dimensional anti-Logita space. And Gary Horowitz, he previously did the computation of holographic conductor, and translational invariance implied some singularity at omega equals 0. Now it can be smeared by introducing a lattice and reproduce the Drude behavior for low frequency and agrees with the experimental result for cupulate for immediate frequency. And Silverstein also considered interesting position-dependent perturbations and found a very novel fixed point and shifted the unitarity bound. Andreas Karch reviewed the progress both ADS CMT and ADS QCD, and he presented the computation of various transport coefficient, and in particular pointed out that for this class of holographic realization, the time scale for hydrolyzation and summarization differ by unfolding time of Baruch geometry, which is sort of a special feature of this class of construction. Now, integrability in ADS CFT is also quite important because this has been very helpful to understand microscopically how holography works. And much progress has been made in this direction. Again, it was sort of a precursor that was visible at the Strings conference in Paris, where Zeitlin gave a description of classical solutions, and Weissert and Zarembo started to talk about the use of integrable spin system to do four-dimensional n = 4 Yang-Mills computation, and pointed out some three-loop discrepancy. And some of these discrepancy was resolved. In fact, more of the discrepancy was resolved 4 years after at CERN. And by this time, there has been really amazing progress in interpolating or extrapolating, should I say, between weak coupling computation and strong coupling computation. Really very convincing microscopic evidence for the holography and ADS-CFT correspondence. At this conference, already Berkovits and Sokachev also talked about the very mysterious dual superconformal symmetry. At this conference, there has not been much talk on integrability by itself, but already gave a very interesting talk relating correlation function to Wilson loop computation. And this is a very interesting feature that is actually inherited from this study of dual superconformal symmetry, although its holographic origin is still mysterious. There has been lots of interesting work in perturbative computation, so I'd like to cover that subject. Again, this subject just started to emerge 8 years ago in Paris. So Dixon started to talk about a very interesting structure in n = 4 super Yang-Mills, and Witten talked about the construction of n = 4 super Yang-Mills computation using string theory in twistor space. Of course, I mean, this was the beginning of this current burst of activities. And this was inherited at the Strings conference in CERN, where Dixon followed up his presentation in Paris to talk about the factorization in spin helicity basis, and Cacciado talked about the remarkable convergent behavior of n = 8 supergravity. Now, final word on this subject is still yet to be spoken, I think. And then there has been some talk about the use of symmetry. Now, this area is really flourishing, and I think that much more to come. We still don't know the full scope of this activity here. Nima Al-Khami Hamed gave 30 minutes presentation of what should have been 30 hours talk. And so he pointed out that the on-shell planar diagram are characterized by permutation structure, which specifies the cells in Grassmannian. So that sort of explains why you get this kind of Grassmannian integral. And this presentation, although he didn't explain in detail, apparently explains the origin of dual conformal invariance, Yangian symmetry, and some of the motivic structures that are very mysterious, and begin to initiate the interaction between physicists and number theorists, for example. And Cacciado presented to me a very interesting new formula for 3-level S matrix for n equal 8 supergravity, but this is not only about planar, because of course it's a gravity theory, so planar does not make sense. Combining Kawai-Llewellyn tie formula and twister in some different interesting CP3/8 space. String perturbation computation is, of course, very important, and it's an important foundation of string theory, as Edward Witten stressed. And so I'd like to remind you that at Strings Conference in Paris, actually, Nathan Berkovitz presented his version of proof of finiteness of string theory using his pure spinor formalism. And there was no talk on this subject at CERN. Now, Ed Witten took the task of clarifying very much of the NSR computation, and there has been some lingering issue about tadpole cancellation and space-time supersymmetry, but I think as far as my level of satisfaction is concerned, his presentation was quite convincing. And of course, whenever he gives a talk, he says things in a way that I never thought of before, but once I hear it, there is no other way, and this was one of the ways. He said that if one asks precisely the question whose answer one needs, these particular questions tend to have simple answer. I wish my research is always like that. Schroeder derived interesting formula for open superstring amplitude at 3 and 1 loop and expressed them as sum of product of Yang-Mills part and string part. This is a very mysterious part, and maybe there is something interesting going on there. Higher spin theory, and this is another area where the burst of activity is taking place, and we are happy to have the founder be present at this conference. And again, this area started, so 8 years ago is a sort of interesting year because basically what seems to be happening is that what initiated 8 years is we are harvesting the progress idea developed 8 years ago. Now, of course, the original idea of higher spin theory dates back to 80s, but Vasiliev gave the first talk at the Strings Conference, introduced us higher spin theories, and there has been talk about higher spin symmetry, and this has to do actually with breaking, which is significant. And I would like to also point out that Rajesh Gopakumar gave a very interesting talk on holography for free theory, but there was no talk on this subject at CERN, but evidently some people were thinking about it for a long time and hard, and there has been remarkable progress in this area reported this year. So, for example, Qin Ying, who is one of the driving force in this area, gave a very interesting talk, so not only about free theory, but in fact, AVGM model apparently has this Vasiliev type presentation. And moreover, not only that, there seems to be a relation between this Vasiliev theory, non-abelian Vasiliev theory, and the string theory in the bulk. And in this picture, it seems like type 2 string is actually bound state of Vasiliev particles. That is very interesting. And Matthias Gabadier discussed the 2 to 3 version of Vasiliev correspondence. And so you have Wn minimal model dual to Vasiliev theory in ADS3. And in this case, the triarity of W algebra, so seemingly different presentation of W algebra on this side and on this side are realized. Here it's asymptotic symmetry of ADS, and here the symmetry of minimal model. And he discussed how these symmetries are related to each other. Maldacena generalized the Coleman-Mandula theorem for ADS4, which essentially says that if you have exact higher spin symmetry, then the corresponding theory is free. However, you can actually break this symmetry slightly broken, and most of the examples that mentioned in the previous slides are of this type. And so those are interesting, and so in that case, 3-point functions are constrained, however, and this gives rise to corresponding identification of ON Chan-Simon plus some free bosons or critical ON models. String model building is a very interesting, important subject, that I should have said. And so there has been actually rather important progress being reported at this conference. I'd like to review that at the Paris conference, actually landscape was the main subject. And the new use of F-theory was introduced at the conference at CERN. And there was actually very interesting talk by Miriam Tvetik presented on this class of F-theory construction. So Miriam computed instanton correction to the F-theory superpotential and found that E8 enhanced point is stabilized by this. And I thought this was very interesting because in the earlier work by Cameron Buffer and the collaborators, this is actually rather a special point, because if we want to have a favorable top quark mass, you want the E6 structure. If we want to reproduce the CKM matrix structure, you want the E7. And if you, on the top of that, want to reproduce neutrino mass mixing property, you want E8. So this type of phenomenologically selected point being chosen by this top-down computation was rather interesting. And Lara Anderson also presented to me what to me is a very important technical development. She made very strong use of Hermitian-Yang-Mills equation. So essentially just U1 bundles, but it gives us a very strong result in identifying standard model-like construction from 10 to the 12 bundles to just 45 by requiring various phenomenological constraints like proton decays. But at the same time, she can use a similar kind of construction to stabilize complex moduli in hidden sector. And the particularly nice feature of this construction was that unlike the case of turning on fluxes, you don't have to do generalized geometry but retain the original Kähler structure. So again, this was a very important technical advance. So I felt that those represented very robust and important technical progress in this area. Hans-Peter Nels pointed out that realistic heterotic model require Higgs and top to be in the bulk, whereas the first two generations tend to be localized, and he discussed that remnant of the original higher extended supersymmetry in low energy effective theory. So now that, of course, LHC is producing interesting physics, it's interesting to see what it implies to the string model building. So Antoniadis gave a very informative assessment of the effort in string model building in the past decade. So I think that these developments are very important. And I think I'd like to say we should recognize that actually this is a very important point, because we tend to lose perspective. I think we should really recognize the magnitude of the task. That is that string theory is a candidate for the final theory. And this is supposed to be the culmination of our search for the most fundamental laws of nature. And if string theory is confirmed, the human's historic march towards the fundamental laws of nature would end. And so it is actually very important for this kind of program to find the connection to particle physics. It is essential for progress. So we should fight hard. We shall fight in Calabi-Yau. We shall fight on the brains. We shall fight in 11 dimensions. We shall fight in 12 dimensions and on the elliptic fibrations. I think that that is important because of in view of the consideration of the promise of the theory. So given that, I would like to quote one sentence, and this is taken from the first 3 minutes by Steven Weinberg. He said that our mistake is not that we take our theories too seriously, but that we do not take them seriously enough. So I really want to point out that we should take string theory, our theory, seriously. String theory is supposed to be consistent theory of quantum gravity, so it's interesting to know what we can learn from that. And there has been lots of interesting talk on this subject at this conference. At the Strings conference in Paris, Mathieu told us about his interpretation of microstate. Hojaba talked about Gödel universe and its potential application to active galactic nuclei. Schenker talked about singularity. And in the previous CERN conference, Gabriele Veneziano talked about Planckian collision, and Strominger talked about extreme curl, and Simeon Hellerman told us about time-dependent solution. Now, what has this conference brought us? Well, Gabriele actually used part of his opening remark to update us on his research on trans-Planckian collision, including string-brane collisions, and Rabinovich discussed crunch in ADS cosmology, and apparently there are two descriptions that are complementary to each other. one with crunch at finite time, another with eternal evolution. So this is very interesting that the seemingly different description gives the same physics. Andy Strominger used the Vasiliev theory to construct an example of Dojita space conformal field theory duality. So this is a very important thing because you need to have some example to make some useful statement, and pointed out the exclusion principle and proposed physical observable in Dojita space. Eva Silverstein, she actually basically talked about two different things in her single talk, proposed the Dojita duality and used it to interpret the metastable vacuum by holographic renormalization group. Now, in her version, the dual space has still dynamical gravity. I'm somewhat mystified whether Andy's version has dynamical gravity or not. But anyway, so it's interesting too that there are some attempts, and in fact, this represents rather a specific proposal, so I think there will be a lot coming out in the coming year. Alejandro Castro shows that sum over geometry for pure gravity in ADS3 does not always work, and works only in very specific case where dual series Ising or tri-critical Ising models. And Rafael Busso assures that if you want to save unitarity, you don't have to die at the horizon. That's very good. Then Freiberger proposed a solution to measure problem in the eternal inflation. And Kostas Bakas tried to realize Randall syndrome localization of gravity by holographic dual of Guyot-Witten domain wall. Apparently, this did not quite work because if you want to do that, somehow brain fattened and get back to 10 dimension. But in meanwhile, he actually found various interesting holographic features of this construction. And we just heard from Kostas Kounas that there are interesting class of string solutions representing bouncing universe. And Barton Tbiebach is developing this double field theory to make T-duality of closed string theory on torus manifest. And it may shed some light on the notion of general geometry, which is still very mysterious. And John Heckman introduced non-commutative space, which normally breaks Lorentz invariance, but his version does not. And he suggested the quantum field theory on this space is gravitational. Still goes on. Now, Sasha Polyakov shows that Dojita symmetry of Banchi-Davis vacuum is broken by quantum effect, and that leads to instability of the Dojita space. And he tried to use that to explain the mystery of cosmological constant. Gomez claims that trans-Planckian scattering in Einstein gravity are dominated by large number of weakly interacting quanta, which he refers to as classicalization. And then he used this picture to describe black hole as condensate of such quantum. So this is a very interesting picture. There has also been a talk about alternative theory of gravity, just to make sure that we know in which market we are in. So Hermann Nicolai gave a critical assessment of various possibilities, such as asymptotic safety, loop quantum gravities, and spin form. So those are all good, except by the time when he came to expose my secret past to the string community that I worked on some of these subjects. So I felt like I was standing in front of the House Un-American Committee by McCarthy or something like that. Now, there has been lots of new insight into quantum field theory, and so these, especially exact results, and exact results are good because it has lots of unintended applications. Want to point out that the strings conference in Paris can integrate a proposed A theorem, and at CERN, Davide Gaiotto talked about this duality on the boundary condition for n equal 4 super-Yang Mills theory, and both of these developers are sort of, again, had important implication at the conference this year. In particular, I would like to point out that A theorem was conjectured 80 years ago, which is now proven by the Komargovsky and collaborators. He also discussed interesting constraint on operator dimension in conformal field theory. Nati Daiberg, to me, was a very interesting talk, pointed out that three-dimensional n equal 2 theory can have anomalies in compact R symmetry with Chern-Simon coefficient with Chern-Simon term with fractional coefficient. And then this realization clarified many things, including F maximalization, and led to a new test of dualities in 3 dimensions. Tudor de Morte discussed class R theory, which includes theory on M5 ring on 3 manifold. This led to 3 plus 3 equals 6 version of AGT conjecture, where these theories are related to 3-dimensional Chern-Simon theory. Yamazaki also talked about related 6 equals 3 plus 3, but started with 4 dimensions. And he talked about 4-dimensional n equal 1 quiver theory, which turned out to be related to 2-dimensional integrable spin system. And there seems to be some hidden relation between Yamazaki's construction and scattering amplitude analysis by Nima Al-Kani-Hamed, and that sounds very mysterious, interesting. I think it's worth exploring further. Davide Gaiotto introduced a notion of renormalization group domain wall relating UV fixed point and IR fixed point, and use it to relate operator in UV and IR. And he showed how this kind of things works in specific example of 2D minimal models. Leonardo Rastelli computed superconformal index for all generalized quiver theory of type A for generic 3 fugacities with or without surface defect. So there has been lots of interesting progress. This year marks 24th anniversary of Whitten's series of papers on topological field theory, including topological string. Next year is 25th anniversary. And at the strings conference, both Andy Strominger and Cameron Buffer talk about OSV conjecture relating topological string finally to something relevant to 4-dimensional physics, the counting of black hole entropy. And at the CERN conference, there was a progress in computing topological string amplitude. At this conference, Mina Aganagic pointed out mirror of resolved conifold is not unique. And this is a new insight that came from the study of not homologies in 3 dimensions. And that may lead to interesting, important insight into not invariant. I think that the complete power of not homology is not understood yet, and this type of geometric picture may shed light on it. So these mathematical developments are very interesting, and in fact, we just had a sister conference in Bonn last week, String Math 2012, and there were like 200 participants there, and so this activity in this interface area of physicists and mathematicians really thriving. I was going to Bonn, and so I actually looked at the very interesting oral history project website of Simon's Foundation. They have an interview of giants in theoretical physics and mathematics, and the Hilsbruch is, of course, one of the had been one of the leading figures in German mathematics in the last 50 years, and was a founding director of Max Planck Institute of Mathematics in Bonn. So since I was going to Bonn, I listened to this, his interview, and towards the end of the interview, which took place December of last year, unfortunately he passed away just a few months ago, interview asked, are there any field in mathematics in which you would like to work? To which he immediately answered, he knew the answer, he said, I would not mind becoming an expert on string theory. And so really this represents a thriving collaboration between physicists and mathematicians in this area. So I'm a little bit running out of time, but I'm going to stop very soon. So I just wanted to give a few overall impressions that I got up by attending this conference. So I tried to find the exact quote, but I forgot to bring the book. So I think Henri Poincaré said that science has its own intrinsic value. But why it has intrinsic value? Because it's universal, its knowledge is universal. Now, how you measure the universality of scientific knowledge? Well, he points out one way to evaluate a particular field is to see how much it is influencing progress in other areas, how much its effect is important. And string theory is certainly doing pretty well on that account by influencing progress in condensed matter physics, QCD, and in particular in mathematics. And in addition to such breadth of impact, the depth and richness of the field are also very remarkable. So, for example, the study of holography and in particular higher spin and integrability is really impressive. We also had very interesting series of talk on supermoduli twister in order to compute amplitude. And there has been several golden ages of supersymmetric quantum field theory, but it seems like we are in one of them. And there has been lots of young people producing remarkable result in exact result in supersymmetric quantum field theories. And also, I would like to say significant progress has been made in understanding how to derive standard model of particle physics from superstring theory. And I think we should take our theory seriously. Personally, I enjoyed that this conference represented more talks with finite alpha prime. I like this because I like alpha prime. And I hope that it is going to be the case in application of ADS-CFT correspondence. Also, because I think this is one of the stumbling blocks that if you want to go beyond qualitative relation to quantitative prediction, you need to control string corrections. And I think it's a hard program, I recognize, but it's important. 3 lessons I think that important to bear in mind. Be willing to modify our goals, take coincidences seriously, and explore generalizations. I'd like to make a couple of observations on string demographic and see, so assuming this represents some really good cross-section of string theory community, so how we are doing. First of all, are we getting younger? Are there younger people coming in, and are we doing a good job in promoting this? Well, this is actually rather difficult because, for example, by looking at the list of speakers of strings conference, it's very hard. I really would have to work hard in order to see their age. By age, I mean the years from PhD, just to be politically correct. And hard to track when they got a PhD. But one thing I can tell very easily is that which one got PhD earlier than me and which one got PhD after me. So I use that as a benchmark. So this is my year after PhD in the past in these three string conference, Strings 2004 in Paris, 2008 at CERN, and 12. So I was actually very happy to be at the top 58 percentile of years after PhD. Now it went down to 48 percentile, and it went to 40% percentile. Of course, the obvious interpretation of this phenomena is that I'm getting old. However, so one can try to make a model and explain. So one model I would propose is that suppose string theorists are active about 40 years on average. There are, of course, people who are active much longer than that. And suppose that they continue to come in as a speaker of string theory uniformly. If that was the case, and if I am to age 1 year every year, that would mean that I should go up 10 percentile every 4 years, and this fits exactly well with this model. So that says 2 things, that is indeed I'm aging. And the second thing is that it looks like there is a stream of young people coming in, because otherwise this model would not work. And then the conference has been reasonably good, if not exceedingly good, but reasonably good in picking them as plenary speakers. I would also see where we are from. So this is actually the diagram that I made at the Strings conference at CERN. I did that because that was the Olympic year. And of course, the US had the largest number of people, and Swiss, which was a host country, and Germans, and went this way. So how about this year? Of course, it is hugely represented by Germans, the host country. And Americans are about the same. There are about the same number of people from the US. I think that I don't see any detectable difference except that the 2 Asian countries have a little bit more people here. And that's understandable because, of course, our friends in Korea are organizing the string conference next year. And so we all thank them and look forward to the conference. Now, after that, we have at least 2 more conferences lined up, possibly the 3rd, although I tried to confirm that, but I couldn't do that, so I didn't list it here. So after the Strings conference in Seoul, the Strings 2014 is scheduled to be held at the Institute for Advanced Study in Princeton. Sorry? Princeton University, please excuse me. And then the year after, it will be at the Institute for Theoretical Science in Bangalore, in India. So we have a lot of conferences to look forward to and exchange ideas. Now, but I'm very sort of sympathetic to those people who will be organizing this conference, because this conference has put impossible standard in terms of organization, as Lars Brink said, the German precision and Bavarian hospitality. So I believe that everybody would agree when I said that wir hatten eine wunderbare Zeit in Munich. And so I'd like to thank Dieter Lust and our friends at Munich. Vielen Dank und auf Wiedersehen. Thank you.